Hi, are we recording? Yes, okay. Hi, I'm Daniel. I'm a final year electrical and electronics student from VIT. Uh, I have a passion in electronics, and embedded systems in VLSI is something I'm passionate about. I have a blog where I do a lot of mostly embedded system projects and using the STM32 F40, and you can read about it here. So actually, today I'm doing something different, something that is outside, I would say, my field, but something I'm very interested in. It's related to the field of VLSI. So I really find these dye images pretty cool, and I always wanted to have a better understanding of them. So today I'm actually going to try and get a better understanding of it. Um, so I'm no expert at dye images or reverse engineering dye images, but uh, from my experience in electronics, you don't have to be an expert. Just start doing it, and then once you do it enough times, you learn. So this is my first die image that I'm going to reverse engineer. So I am actually going to use a die image of a 555 timer. This one. Okay, this is the image that I'm going to be using. So firstly, what am I doing? So this is a 555 timer IC, and the 555 timer IC is implemented in the die in an image like this. And we are going to take this image and try and get as much information as we can. Now, I don't expect to get a lot of information, but I do want to get as much information as possible from this image and try understanding how it works. So this is the image that I'm going to be reverse engineering. So die images are images of anything. So even your processor in your computer would have its die image. So something like the 6502 has, so see, this should be a lot more complicated, as it has here registers, adders, buffers, and uh, so the individual transistors as such is a lot smaller. So that's what we're going to do. We're going to figure out from the transistors what the logic it implements is. So my inspiration for this project is actually this blog by Ken Sheriff. I would suggest you take a look at this. It's quite a interesting. I think my screen recording. Okay, still here. Sorry. uh, this blog's pretty interesting. What he does is he takes apart this chip. Sorry, so he gets the IC, he decaps the IC. So first let's talk about decapping an IC. So there's a very cool YouTube video. See, decapping, where so you get ICs in these dual inline package, and so this is the video I was talking about, where he goes ahead and he removes the plastic coating. So he goes ahead and removes the plastic coating with some nitric acid, and then what he gets is the die image. So this is a really small, few nanometers across. This is the die, and he, sorry, so yeah, this is the die image. He takes it and then he puts it under the microscope, and should go ahead here, puts it under the microscope and takes images. So they don't actually just take one big image but many images and then stitch it together. So here, this is the package. This is your 8-pin DIP package, and inside this is the die. This die. So we use this 555 timer or other ICs like this pretty often in electronics. So I'm just using the 555 as it's very popular and there's a lot of documentation on it. So this, I would say, is my biggest resource. This is a site called Richie's Lab where he has many 555 timers which he has taken apart, decapped, and taken high quality images of. So this is one. There's many. There's quite a few bipolar types as well as CMOS types. Uh, so I can show you this one, the original one. So as you can see, what he's done here is he's gone ahead and reverse engineered it, in the sense he's got information from the die image. He's identify the transistors. So that's what I want to do. I'm going to use this image, this IC. So this is the IC I'm using, and this is the image I'm going to reverse engineer. I've just downloaded and kept it, and that's what we're going to be doing today. So I'm using a bipolar type because they're a lot easier, but there are CMOS technology which is more popular. It's the newer technology. CMOS stands for complementary MOSFET. So there's a PMOS and an NMOS. So as you can see, this is actually a bit more complicated to reverse engineer. So as it's my first chip, I thought I'll go with something simple. So what? Whoa, so this is what we're doing. This blog is inspiration for my project, and I can show you. So he's taken this image and he's gone ahead and created this pretty cool interface where he mapped each part of the image out to the circuit diagram. So if you want to see where, say, this transistor, we'll see where this transistor is. If we select it, you can see that transistor is that. Or if you want to see what is this pin, you can see, oh, that's a control voltage pin. This resistor, what it does, and there it is. So you can see something like this is okay. So this is my inspiration for the project. So let's go ahead. Why I'm using 555 timer? Because it's actually very popular. The actual working of a 555 timer isn't very important for our purpose, but if you ever want to know the actual working, I would suggest this video. If you watch this video, you will definitely understand how a 555 timer works. And I'm not going to try and explain the working because I can't explain it as well as him. If I do, I'll just be copying. So I would suggest this video. So rather than actually talking about the 555 timer, I thought we get straight to it and actually start reverse engineering this die image. So the first thing when you get any die image is trying to identify the significant. What can you identify patterns or anything. So I can see there are, I would say, pads. There's 1 2 3 4 5 6 7 8 pads. That's good because a 555 timer, if you know, is a 8-pin package. So the 8 pins, 1 2 3 4 and then 4 on the other side. So that's good. That's we don't know which pad is for which pin, but now we know that. So these things are probably pads. Then what else can I see? I see 3 Christmas tree kind of things. So there's one. My cursor isn't very visible, is it? There's one here, and one here. These are, I don't know what it is. But we know it is 3 things. It's probably transistors, but then why only 3? We'll figure it out. But that's what I want to do. So first we're going to figure out the pins. So these are the pads and they're connected to the pins via something called a bond wire. So you can see in this figure, there's the pad and the bond wire, and the bond wire goes to the metal contact which is outside the IC. So So we know we have 8. Now we have to correspond each pad to one of the 8 pins. So what I do is I go for ground. So the ground pad is normally the easiest to figure out because it tends to go all along the chip, because ground is required all around the chip. Like the whole chip requires ground. So if you look here, see, ground is required to connect it to all these parts, this part, all these parts here. So ground tends to go all around the chip. So I would say that this pin seems to be going all around the chip. So I'm going to say that this pin is probably ground. So I might be wrong, but for now let's just say that that is ground. If you're wrong, we can always come back. Let's fill this actually. Let me say that's ground. Just gonna go ahead and fill in all the other pads. I'll be back in a minute. So I'm just filling in all these pads, as you can see here. It's just ending here. These are all pads. So now we have our 8 pads marked out. Now we got to figure out which pad is where. So I said that this is ground. If it's ground, then let's find a pin out for this circuit. So I found the pin out here. So they say ground is pin 1. Okay, so we're going to say that this is pin 1. So that means this would be pin 2. Actually, either this or this. I'm going to say this one. I'm going to say this one is pin 2. We'll see. And if that is, then that means this pin over here must be pin 3, pin 4, pin 5, pin 6, pin 7, pin 8. So I'm just going to mark those out. Okay, so like I did, I just marked ground 2, 3, 4, 5, all the pins. So let's just go back here and we see that pin 8 is VCC. So this pin should be VCC, which seems right because it does seem to go. VCC also needs to go to quite a lot of connections, and it seems to have a broader path. As you can see, it's a broader path. So that might be right. But we can't be sure yet. So let's go on. So we are going to. So that's the first step. We found the first significant thing, and we marked it out. Now we find the next significant thing, which are these 3 big things. So what are they? Probably transistors. So here I'm just gonna go ahead and find these out. And okay, so this is a high current transistor for discharge pin. This one's for discharge pin. This is for the output high, and this is output low. So these 3 are high current transistors. So basically what they mean is that there are other transistors, but these are transistors that require a high output current. And from electronics we know that, to get a high output current we require big size. So we're going to say that these 3 are transistors. And if you go ahead and read more into this, you'll see that here it's the collector, base, and emitter. So wait, should I just go ahead and tell you what a transistor is first, in case you don't know? So a transistor is a very simple thing. It's basically a switch. So we have 3 terminals: the collector, the base, and the emitter. So I think of it as a switch between the collector and the emitter, and the base is the switching thing. So if we turn the transistor on, that is provide some voltage to the base, then it turns on and connects the collector and the emitter. If you don't provide anything here, then it stays open. So these 2 aren't connected. That's what it is essentially. So the base is what I would call, that's the middle region. That's the switching region. So let's go here. Let's start with this one. So I'm going to say that this area here, I can probably fill that. I'm going to use let's use green. Okay, green for the what is this, collector, right? So I'm going to use green and say this is the collector. Color it in, sort of like connect the dots, or coloring within the lines, right? Yeah. So here you go. So that is the collector, and that would mean that yellow would be the base. Oh, I messed that up. My bad. I messed that up. So actually, green's the base, yellow is the collector, and let's go for gray as the emitter. So we're saying this is the emitter. Okay. And okay. So gray is the emitter. Now what happens? We can see that the gray is still connected. It's connected down, 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 and it's connected to pin 3. So see, this gray is also connected to pin 3. So pin 3, let's go see what pin 3 is. Pin 3 is actually output. Okay, makes sense. They said that this is connected to output low. So okay, fine. This connected to output high. Let's not sure. Let's look at this. This here pin 3 is the output pin, and pin 3 is connected to two transistors. So it's either Q22 or Q24. We're not sure. I mean, it's either one of that. But wait, if it's Q22, then where's Q24? Sorry, this might be Q24 then. So this gray thing is also connected to a collector. Oh, it's not as neat. Yeah, the same pin is connected to this emitter as well as this collector. Okay, so let's see if that checks out. Here, so you see this emitter is connected to pin 3, which is connected to this collector. Okay, wait, that makes sense. That makes sense. So this must be Q22, and this must be the output pin we have here, and Q24 must be this. Okay, uh, just confirm that. Let's see where the emitter of Q24 is connected. It's connected to ground, so that means the sorry, here this must also be connected to ground. Is it connected to ground? We go, let's follow the lines. Go with gray itself. Follow the lines. Follow the lines. Yeah, it is connected to ground. See, so we reached. So yeah, so Q24 is connected to ground. So this is probably we found the right thing, right? This here is this Q22, and Q24 is this here. So the emitter of Q22 is connected to the collector of Q24. Is that right? Yes, it is. It's connected through pin 3. Yes, which is output pin. Yes. And is the emitter of Q24 connected to ground? Yes, it is connected to ground. Here we go. We did some reverse engineering. We found what these two parts are, right? And that's pretty cool. I found that actually was a lot of fun. So I can go ahead and color this in. Just give me a minute. Okay, so I color that in, and okay, so cool. We found two things. So now let's go see what the other one was. There's one more here, right? What is this? Let's see. It seems to be connected to pin number 7, right? Because pin number 7 seems to be connected to the collector of this transistor. So let's go see what pin number 7 was. Pin number 7 is the discharge pin. Let's go to this diagram. The discharge pin is here, and it seems to be connected to the collector of this transistor. Okay, and then there's the base which is connected there, and the emitter which is connected to ground. Okay, let's see whatever the is connected. The emitter seems to be connected here. I just seems to be connected like this, and seems to be connected like that, like that, like that, like that, like that, all the way here. And yeah, I think it is connected to ground. Yeah, you can see it goes all the way to ground. So we are right. So this part is connected to ground, and the collector is connected to pin 7. So, and pin 7 is the discharge pin. So as you can see, pin 7 is the discharge pin. So this seems to be Q14. This is Q14. Not bad, not bad. I think that's pretty cool. We identified another transistor. I identified Q14. So what we identified right now were the three big high current transistors. Oh wait, if we go back here, and they said that this one was discharge pin. There you go. High current transistor for the discharge pin. So we are right. So it is connected to discharge pin. Pin 7 is discharge. So you can see, now let's look at the differences actually if you want, between, just can zoom out a little bit. There you go. So between this die shot and this IC, you can see here it's quite different. The three are placed like this. These two are the output, and this is the discharge. Here, these two are the output, and this is the discharge. So, okay. Yeah, so we seem to have got that. Another thing we can do now is actually go, we know pin 8 is VCC, right? So it's written here, pin 8 is VCC. So we can see VCC seems to be going inwards somewhere, and we also do know that Q22, which we've identified, Q22, the collector of Q22 is connected to VCC. So that means that this yellow area should be connected to VCC. So let's just go follow the path and see if that is true. Let's go ahead. See that. Yes. Okay. Seems about right. Going like that, yeah. Seems about right. And go down through that, and oh, we reached pin number 8, which is VCC. So we're right. The collector pin is connected to VCC. Cool. So yeah, we have identified quite a bit now. I would say that the three big things we have identified. Let's go with something. Okay, now actually, you know what? Let's do. Now we know that this is a 555 timer. So what does that mean? That means that there are three 5 kilo ohm resistors. 1, 2, 3. And here, see this R1, R2, R3. All three are 5 kilo ohm resistors. So we know there are three 5 kilo ohm resistors. So let's go find them. Now, resistors aren't very easy to find on die shots, but if you look pretty hard and you know what you're looking for, you might actually find it. So I found it here. Let's go and find it in this image. Let's see here. Where's the 5 kilo ohm resistor? Oh wait, here. This one. Let's see where this is in the die shot. Okay, it's here. Oh, so this is what a resistor looks. Now we have to find an identical image of this. There you go. So that's the other 5 kilo ohm resistor, and there should be one more. There you go. That's the three 5 kilo ohm resistors. Okay, so let's try finding that here. I see it. I see three lines. Let's go with a pink, and let's draw it out. See if you can see it too. Here I see this line as it's a straight line. It should be easy to draw. Oh no, yeah, got it right. That's one. This is the second one. Just bear with me here. Up to here, and that's the third one. So resistors, they are just straight lines. They don't have to be straight, but they're just lines in die images. Here you go. So this is 3. Now actually we know that these 3 should be connected in series, right? Because one is connected to VCC. So let's find which one is connected to VCC. VCC was here, and this one, this is the end of the resistor. This is the metal contact. It seems to be connected to VCC. Okay, so this is connected to VCC, and the other end of this seems to be connected to the end of this. Okay, so one end is connected to VCC, the other end is connected to the other resistor, and now the end of this resistor is not connected to the first one. So we know that it's not in parallel, it must be in series, and it's connected to the third resistor, which seems to be connected up here, which is connected to this brown thing, which was ground. Is that right? So that's 1, that's 2, That's 3, and the third one is connected to ground. So we're right, we've identified the big three big resistors, the three 5 kilo ohm resistors here, and we identify that it is in series with one end connected to VCC and one end connected to ground. Uh, okay, so that's good. Now I would actually say that that's most of it. I don't actually see anything else that's very significant. I see stuff like this. So if I just take black, this 1, 2, 3, 4, 5, 6, 7, here 8, 9, 10, 11, 12. These are transistors actually, but how is this transistor different from this or from something like this? Well, these are PNP transistors. So let's go to Ken Sharif's blog and see these. These are PNP, and this here is an NPN. So if you look, that one, that's an NPN. Well, this is a PNP. How do you identify the difference here? Is the arrow going in is a PNP and arrow going out is an NPN. The arrow is always on the emitter. So this goes actually p-dope materials are less mobile than n-dope, but yeah, it's not as important. Now if we go here, we've identified the four. Let's look at one of the pins. The pins are easier to get across from. So this is pin 2. Let's see, why not, let's go with pin 6. Okay, pin 6 seems to be isolated. It seems to be only connected down this line, down this line, down on here, and seems to be connected here. And you can see there's a break here. So this, I would say, is a transistor, and then there's one more transistor connected. So let's see, what is pin 7? Pin 6. Pin 6 is the threshold pin. Threshold pin is here. And yeah, it is connected to Q1, which is then connected to Q2. And this configuration is called the Darlington Pair. See, look, it goes here. This would be Q1, and this is Q2. And I would say that this is Q3 and this is Q4. And they seem to be connected up here to pin 5. Let's see what pin 5 is. Pin 5 is a control voltage. Are there? Yeah, it is. Look at this. So this Q1, Q2, Q3, Q4. Q4 is connected here, which is connected to the control voltage. So I think we got it. I think we got that right. So I would say that's Q1, that's Q2, Q3, Q4, and connects all the way up here to pin 5, which is also connected to, oh, check that out. So look at this, pin 5 is connected in between the two 5 kilo ohm resistors, right? It's connected here. Now we go look. It is connected between, pin 5 is also connected here between the two 5 kilo ohm resistors. So we're pretty confident with that analysis. So we've identified Q1, 2, 3, 4. Now we can actually go, and there aren't too many transistors to identify. So one thing I like to point out are these PNP transistors, Q5, 6, 7, 8, 9, 19, 20, 21. They're all what I would call current mirroring transistors. So if you go here, yeah. So basically just a current source. They're not very important. It's a way to control the current source. So I would actually say that this 1, 2, 3, 4. There's 1, 2, 3, 4. Yeah, there's quite a few of them. Something here. Let's check this one out. So there's ground here. Let's take gray, and is it gray? Yeah, gray. Gray is connected around here to this transistor. So which transistor is connected to ground? Let's check which transistor is connected to ground. It could be Q17. Q17 is connected to ground. Q10. but Q10 is connected to the trigger pin. Where's pin 2? No, so this is probably Q10 then, right? Because pin 2 is the trigger pin. It's connected here, which is also connected to ground. Okay, so this I would say is Q10. Any other transistors connected to ground directly? I don't see. Q7 maybe? Q7 seems to be connected to ground. Or it could be Q17. Q17, Q18 are connected to ground. So this could be Q17 or Q18. Uh, we can't be sure. We can't be sure. But these are NPN transistors. This is a PNP, so it's probably this. Well, this is a PNP, right? Now this circuit diagram doesn't have to directly represent this die image. It's not the circuit diagram of this die image, so let's not stick with that. Uh, what else can we identify? So we can see a lot of these resistors here. So these are resistors. If I go, let's go and see some of what Ken Sheriff found. So he said all these lines, they are resistors. Can I select? Yeah, this seems to be a resistor, right? Is it a resistor? Yeah, that is. 4.7 kilo ohm resistor. So if that's a 4.7, then a 330 ohm must be a lot smaller. Yes, I know that. Yeah, there you go. So it's a lot smaller compared to the 4.7. So this is also 4.7. There you go. So this and that were approximately the same length, I guess. This is a 1 kilo ohm resistor. Where's that? That's there. It's a lot smaller. So 5 kilo ohm resistor. So this is one of our main 5K. So let's look at this one then. 6.8. It's bigger than a resistor. So it's actually curled up here. Goes like that. Curls around all the way. So yeah, those are resistors. Resistors aren't very easy to figure out, so I'm going to actually leave the resistors. Let's go with some other pin. So this pin 2 we said was trigger, so this was pin 2. Pin 3 was the output. Let's see what pin 4 is. Pin 4 is reset. And where's pin 4? Where's the reset here? Connected to Q15. This is probably Q15. Pin 4 is connected here. So this transistor here is probably Q15. Q15 seems to be connected to Q14. Wait, which is Q14 again? This one, right? Q15, yeah, they connected, must be connected. Q15, Q14. The transistors aren't very easy. Which part of Q14 is it connected to? It's connected to the base. The base is this gray thing. So then our transistor might actually be somewhere else. There is no transistor here. It's very hard to actually recognize transistors in these, especially once I drew over them. It became a lot more harder. But we can see a lot of resistors, so I'll show you one other resistor. Let's take pink again. Here, this is a resistor. Goes like this. Goes like that. Through that. It seems to be connected here. I don't know which resistor it is, but it is one resistor I've identified. So these are transistors. This is one transistor. This is another one. This is another one. This is another one. These I would say are the voltage, the current mirrors. I would say these four, Q5, 6, 7, 8. These 1, 2, 3, 4. They seem to be connected to a resistor and then connected to VCC. So how they connected to a resistor? You can see these right. These resistors then would be connected around here to VCC. Here, here. Yeah. So we've identified those. Now what else can we identify? What's pin 5? Forgot what pin 5 was. Pin 5 is control voltage. We identified that. We identified pin 5, we saw that it is connected here to this transistor. This was these 4 transistors. Then pin 7 is the discharge pin, right? Yeah, which is connected to Q14. So we identified this as Q14. Q8 was VCC. Q2 was, pin 2 was trigger pin. So this seems to be 10, 11, 12, 13. Are these are also voltage, current mirrors. So these 4, I would say, are these 4. They seem, because they're all PNPs, right? All PNP. So these 4 are these 4 transistors here. Seems to be connected to ground. Is it connected to ground? One of these. Yeah, Q10 is connected to the ground. So I would say these 4 we have identified. As well as these. Let's see if we can find these. Oh yeah, these I did identify. These 4, right? 1, 2, 3, 4. And finally we have this part of the circuit. There's not much. We have actually identified most of the circuit. So to recap, what I did was I first formed the pins. I found which pin, assigned a pin to a configuration. Then I found the next most visible thing, which was these 3 transistors, and I actually found out what the transistors did. I checked the connections, and after that I drew VCC and ground and drew the connections of VCC and ground. So I saw where ground went, I saw where VCC went. So VCC is going around here too. So I said that it was this, right? Yeah, so it seems to be connected to VCC. So now the thing about the 555 timer is these are just 3 equal valued resistor. Look at here. This is an easier. So these are 3 equal value resistors. The value here at this point is 2 by 3 VCC, and the point here would be one third of VCC. And these are just 2 comparators. So a comparator, I'll explain the working. If you give me a minute, I'll find it. I have this image downloaded. Okay, let's open Paint. Okay, so what I said was the value at this point between these 2 resistors here, it's one third of VCC, and the value here would be 2 thirds of VCC, and basically they used as reference voltage and fed into this comparator. So working on the comparator is pretty simple. I'll just mark the positive and the negative. So this is the negative, this is the positive. And the first time I heard of comparators were in op-amps. And an op-amp, an open loop op-amp with no feedback, is basically a comparator. What it does, it compares the inputs and it produces an output. So if the negative input is greater than the positive input, then it produces a high output, otherwise it produces a low input. Sorry. If the positive is higher, then it produces a low output. So basically there are 2 comparators, and they are fed into a RS latch. Now RS latch is pretty simple. There's a reset and a set. If you set it, then the output is high. If you reset it, the output is low. And there's a external reset as well. And this is just fed to an output buffer, which is either high or low. So what this transistor, which is connected to VCC, pulls this output high, and this transistor, which is connected to ground, pulls the output low. So it's either this one which will pull it high, or this one. Either one of these is on. If this is on, the output's being pulled high. If this is on, the output's being pulled low. And this we identified as the discharge transistor. You see here, the discharge transistor, which is connected to ground, That's this. We see that it is connected to ground. It's connected to discharge pin. So that is that. Uh, so when you implement this RS latch as a in transistors, you would get this. It's pretty simple. One, two, three. These three transistors, this diode, and two resistors. This is what implements an RS latch. So that's somewhere in here. They're pretty small to see. It's I would if it was my guess, I would say it's somewhere around here. The RS latch, and that one, two, three. It's connected to both the output transistors. Uh, so I think this is not bad. We've done pretty well. We've identified quite a few components. Uh, this is my first circuit, so my first die shot. So I don't expect too much more. I'll just go ahead and mark out other things we have identified. We identified this transistors Q14. We identified all the pins. It did make sense. Like a lot of the transistors did make sense. So we did identify this as 1, 2, 3, 4. We identified these 4 as well as these 4, which are these. I said, yeah. So these 4 are the 4 in the middle. So as you can see, they are connected to VCC. Let's just zoom in here. So this is also connected to VCC. VCC goes down here as well, connected to this resistor. Yeah, that's good. Is there anywhere else where VCC goes? No, it seems to only go there. It's probably connected through transistors or resistors, which I haven't found yet. Yeah, this also VCC. This is all ground. Oh, just take the black and continue. Here, here, here. And that pin goes to pin number 5. I'm right. Goes like that. Here. To the control pin number 5, which is the control pin. You go here, and the pin number 5 is also connected to both the resistors. Like I said, pin number 5, it's connected here as well as down here. Oh, don't know what else to identify these transistors as 1, 2, 3, 4, 5. Is there anything I can get from that? Okay, this seems to be connected to ground. This one's connected to ground. Like that. There's 1, 2, and the output seems to be connected here. If I had to guess, let's say that's the it might be around here, these transistors. Yeah, might be these transistors. These transistors seem like it. 16, 17, 18. I would say that this would be 16, 17, 18. Is it connected to ground? 16, 17, 18. Yeah, 16, 17, 18. See, they're all the emitters of all 16, 17, 18 is connected to ground, and you can see I just drew ground right through them. So yeah, I'm pretty confident that that's 16, 17, 18. It could be these as well. This also seems to be connected to ground. This one as well. So these two. Oh, yeah, those as well. So I think, yeah, we've got a good idea of what a 555 timer implemented as. You can see the 3 5 kilo ohm resistors, all the pads, the ground and VCC, the 3 high current transistors, few small NPN transistors, and few PNP transistors with access current mirrors, We saw how one pin is connected to another pin through few transistors. I thought this was actually pretty cool how we found that pin 6 and pin 5 are connected. We found it in the die image. I genuinely found it in the die image and then checked the actual schematic and found out that they are connected. Pin 5 and 6 are connected. Not directly, but yeah. Uh, so this, I think, concludes our video for today. I do seem to have identified quite a bit. For my first dash out, this is not bad at all, I think. Obviously we didn't identify all of it. Not completely happy until I identify all of it, but there are limits to what we can do. Uh, yeah, that's pretty good. So I would suggest again to check. We can check. Actually, let's take a look at all the other 555 images. So, sorry. Here again, you can see 1, 2, 3. These two seem to be connected. See the base. Sorry, the emitter of this one seems to be connected to the collector of that one. Again, similar. We do see these 3 resistors down the middle. Okay. Again, this one again 1, 2, 3, and I see few lines down the middle. Again, same thing I see. Here it's because of the etching that it is connected. It's actually 3 long lines. The gaps just because it got etched away. Again, same thing here. You can see the 1, 2, 3. This I would guess would be the output pin because it's connected to 2 transistors, one to turn it high and one to turn it low. So yeah, this is the chip we looked at. I think there's quite a few. You can take any one and go ahead and try and identify whatever you can from it. Okay, this seems very similar to ours. Again, is this the same one? It might. No, it's not the same one, but it's similar. So again, you can see that this pin seems to be connected here. So I would say that's pin 7, and this pin would be the output pin. This would be the ground. This image is very similar to the one we did. This is VCC. Yeah, this is pretty similar. And again, I would identify the same for again the big 3 kilo ohm resistors. So actually, once I've done this one which is very similar, you can probably do it. It won't be hard at all. But there are many images. So if you look and see what this guy has done, he's found his 3 5K resistors. He has identified the collectors normally given in red, and you see he sees that it's connected there. Another thing I found cool was how we identified that the resistors are in series. So how we saw that this end is connected to this end, and this end is connected to this end. This end is connected to VCC, while this end is connected to ground. I found that pretty cool. It's cool figuring it out from the image as such. Getting this, if we were pretty talented and if we spent a lot of time, we could probably get this image back from this image if we had a lot more knowledge. Yeah, I think that's all. This is a pinout, and you can see how the 2/3 VCC and the 1/3 VCC across the 5 kilo ohm resistor. So another thing is the 555 timer. People assume that it comes from the 5 kilo ohm resistors, but he says that it's just arbitrarily chosen. Okay, never mind. It doesn't really matter how the name came. And it's actually what's most important is actually understanding how it works, so you could use it later. And it does work through charging a capacitor here and discharging it through resistors through an external circuit. And it's quite a simple circuit with just basically 2 comparators, a voltage divider, and a flip-flop, as well as a discharge transistor. So again, I would suggest you to go watch that video by Benita. But I hope you learned something here, and I'll see you for my next reverse engineering chip.